Hello everyone, welcome to our talk and thank you for being here. I am Damiano Melotti and together with Maxime, Rossi, Bellom, my colleague at QuarkStub, I will present our research on Titan M, a security chip recently introduced by Google in their Pixel smartphones. But before starting to talk about this chip, let's first understand why it is used. So it is in the recent years that vendors started to rely on specialized hardware to improve the security of their systems. There are mainly three ways to do so. The first one is the one of virtualized solution. One of the main examples is ARM Trustzone. In that case, the same chip will enable two execution modes, and one of them can be the secure one. Then we have on-chip solutions, such as the one that Apple is using with their secure enclave. In that case, on the same system on chip, there are two different chips. One of them is the secure module, and finally we have external solutions, and that is indeed the case of Google Titan M. So for Android, it was quite common to use. It is quite common to use ARM Trustzone, but an external module brings better tamper-resistant properties than a virtualized solution. So this is actually the reason for which Google decided to create this new solution to improve Trustzone's level of isolation. So here it is, the Titan M. It is a very tiny chip that you can see here from this picture of a teardown. It is a chip generally used for the management of secrets and critical information for the security of the device. We can think of several trusted applications that are hardware-backed, such as StrongBox for key generation or key attestation, ADB for secure boot. There are more, and the list can evolve as Android evolves. So in general, the most secure APIs that require the highest level of security are backed on Titan M. So you may ask, why is this chip so interesting? And first of all, there is really little available knowledge about it. When Google announced it, they claimed that they would publish the sources, but this never happened. More than that, there is no existing paper or conference presentation or blog post. There is only one CVE write-up that is on the crypto behind Titan M. But in general, this feels to be a bit outside of the radar of the security community. So we feel like there is a research gap, and we want to fill it with this research. With this research, indeed, we want to understand how the chip works and how it can provide the security APIs that it offers, if it is really so inviolable and secure as it seems to be. So to do so, we will start from the chip's architecture and its internals. The chip is based on ARM Cortex-M3. The system on chip has been hardened against physical attacks with some special defenses. So there has been a hardening on the hardware level, and also there are in the chip itself some external modules to perform specific operations, such as random number generation or cryptographic operations. Then the chip communicates with the rest of the world via some buses. Two interesting ones are the UART for logging and console, and then the SPI that allows to effectively communicate with the main processor and the Android operating system. The firmware of the chip can be found in the Pixel file system. Quite surprisingly, this firmware is not encrypted nor obfuscated, so a researcher can immediately start reversing it. And it also presents some debugging strings to help in the reversing process. Here we have the path in which we can find the file. And we can immediately notice that there are two sections, we call them A and B, that have to do with the A and B update mechanism. This basically means that one section can be up and running while the other one is being updated. Each section is formed by two images, RO and RW. RO is the loader, while RW is the main OS. Outside of the firmware file, there is also a boot ROM that is mapped at address 0. This is not available, again, in the firmware file, but is present in the chip. And it performs the initialization, the really early boot phase. Then we have some dedicated regions for persistent data and some hardware registers that are mapped in memory. Titan M has an operating system that is based on EC. EC stands for Embedded Controller, and it is an operating system developed by Google and fully open source. This operating system is written in C, and it has some interesting properties. First of all, it has no dynamic allocation, so everything the memory has to be managed at compile time. It is built around the concept of task. There is this execution unit that takes together the features of the chip, and interrupts allow to switch from one task to another. Tasks in total are 9. 2 of them are also present in EC, idle and hook. They have to do with general management of the chip and the system. And then there are the specific tasks of Titan. Nugget is the main one. And then we have a series of what we would call trusted applications. So those applications that allow to have hardware support for some specific APIs. AVB, for example, again, for secure boot, face auth for biometrics. Again, this is a list that can evolve over time if new features will be added to the system. And finally, we have a console task that is the one responsible for handling logs and the communication via the UART console. At boot, the loader, so the RO image, will have 2 choices, 2 images from which it can boot, and it will choose one first based on the version number. So it will choose the most recent candidate. Then it will check if the magic number on the header is present and is indeed matching the right value. It is a -2 if we take it as a signed integer. And then it will verify the signature that is taken from part of the header and the entire code of the image. If this is fine, then the image is effectively launched. Otherwise, the other candidate is chosen. There are 2 ways to, let's say, change the firmware. Regular update is the first one. It is implemented in the Nugget task, and it effectively allows to change the firmware. There are 2 commands involved in this procedure. The first one allows to write on the flash and overwrite the image that is not currently run. And this command will invalidate the magic number so that it will not boot immediately. And then with the second command, this magic number will be set again, but requiring a hash that is derived from the user password. The second way is represented by the rescue feature. This is instead implemented in the loader, and it allows to only flash the RWA image while deleting the B section entirely and the user data stored in the chip. This feature requires the image to be in a special format called rec file. And here we have on the right a representation of the packets with a header and footer with the hash. And this feature is only accessible in fast boot mode. From the security point of view, the firmware is, first of all, has a secure boot. So as we have seen, there are signatures that are checked at launch. There is no memory management unit, so things like ASLR, code relocation of any kind are not possible. But there is a memory protection unit that allows to divide the memory into different partitions and assign different attributes and permissions to these regions. Also, the firmware is very simple, as we have said before. Having no dynamic allocation eliminates directly the presence of some classes of bugs. there is only one software protection, which is also quite interesting to see. It's a hard-coded canary that is checked when the scheduler switches from one task to another. So canaries are a well-known exploit mitigation technique. However, the fact that the value is hard-coded makes it quite easy to bypass. We are not sure whether this is indeed a security property or if it was only implemented to detect errors or faulty states. The communication with Android takes place using Protobuf, a well-known serialization framework also developed by Google. This is language agnostic, and specifically Titan M uses the NanoPB project to encode and decode messages. These messages are available because they are part of the Android open source project, and the fact that the Protobuf is being used is yet another interesting property from the security point of view, because it reduces the risk of input validation bugs, since the primitives are provided by this dependency. So let's take, as an example, one specific task and one specific feature of Android, that is StrongBox, which is the hardware-backed key management API available in Android. Now, StrongBox behaves in a quite similar way to what was done with Trustzone. So Titan M does not store any key, but it only generates them and then encrypts them with a key encryption key to allow them to be stored as key blobs inside the Android file system. So this means that the root user on the Android system can effectively impersonate any app and use any key by sending it to Titan. But again, a root attacker cannot extract the keys. So StrongBox uses this key encryption key to encrypt the keys. It is built upon several components. Two interesting ones are the root of trust. There is a SHA-256 digest sent by the bootloader when the chip is reset or when the phone is reset. Also, we have a salt that is locally generated, again from random, on the Titan M when a root of trust, a new root of trust is provided. These values are stored in an area called SFS that will become interesting later on in the presentation. So I will now let the floor to Max, who will introduce the tools that we developed during this research.
We are now going to present a set of tools we implemented to help us in our research. The first tool we made is a Ghidra loader whose role is to load images from the firmware file at the right addresses in Ghidra. And we can do this because the firmware file is in fact unencrypted and present in the smartphone's partition. And also thanks to some headers present in AOSP that describes the image header and gives an idea of the flash layout. Our loader will also create the memory regions that are needed by the firmware file, such as the RAM or regions where you will find hardware registers maps. And because EC is open source, and also because there are a lot of strings present in the firmware, it is in fact not so hard to reverse statically this firmware. However, there are some parts that are more difficult to understand, such as the state machine of the tasks. And for that, it would be really helpful if we could dynamically trace the commands that are exchanged between the Titan M and Android. So we were wondering where to hook in the Android system, and we decided to hook to instrument the Android daemon Citadel D. Indeed, this daemon is central in Android in the sense that every Android components who want to communicate with the Titan M have to send packets through the Citadel D daemon. So we use Frida in order to hook a function called noseCall application, and this function has to be called whenever there is a command sent to the chip. And thanks to this script, Frida script, we can now see the command exchange between the Android services and the Titan M. And this is an example of what we can see thanks to our script. Here, the command is add RNG entropy, and we can introspect all the fields of this command, such as the app ID. In this case, it's 2, and it corresponds to the task key master. And we can also see that the row bytes of the request and that the reply is empty. But it is not very convenient to use a FRIDA script to send messages, to send command to the Titan M. So we created a client that we call nose client that will send, that allows to send commands without by bypassing the Citadel daemon and by communicating directly with the kernel driver. And our client is using the protobuf definitions that are public in order to generate the commands data, but also to display in a human-readable way the results sent by the chip. So now, thanks to our tools, we can send commands and sniff the commands that are exchanged when Arduino booted. And this is, in fact, the limitation of our tools, because there are some interesting commands that are sent by the bootloader of the main CPU to the Titan M. For example, the root of trust is provided by the bootloader of the main CPU. And while reversing the firmware of the Titan M, we discovered that in some command handlers, there are some specific checks in order to see if the main CPU is in bootloader mode, otherwise the code isn't executed. So to address these limitations, we tried to look directly for the SPI bus on the hardware level. And at the beginning, it was a stupid bet taken by the other author who is not there today. As we were struggling to find the SPI bus by other ways, he proposed to solder each of the 64 pins of the Titan M onto the breakout board you see on the right, the green PCB, and then solder back the 64 pins of the from the PCB, from the breakout boards to the footprint of the Pixel 3 on the Pixel 3. And so, as you can see, he succeeded, and he deserved his title of master of micro soldering. And what is cool with this setup is that, first of all, it works, the device boots, and it can communicate with the Titan M. And on top of that, we can place probes to sniff the signal on on every pins of the Titan using tools such as a logic analyzer. And thanks to that, we have been able to guess the pinout of the chip. So this is the result of this guessing step. And the first thing you may notice is that we identified the SPI bus. You can see the green boxes on the right of the matrix. We also identified the UART pins, but the UART is also exposed on the phone PCB, and it is more convenient to use it directly on the PCB of the smartphones instead of desoldering the chip. We also identified 2 pins of the USB bus that you can see on the left of the matrix. And this USB bus seems to be accessible through a debug cable called SUSI cable. And when using this cable, the UART console becomes available through USB. Another point of interest is that the buttons, the physical buttons of the smartphones are directly connected to the Titan M, so it can detect when one is pressed on the hardware level. And some of you may wonder why there are so many white pins, white boxes. In fact, we believe these are not used and that there is nothing behind on the PCB of the device. While for the yellow ones, it seems that they are connected to something, but we still don't know what it is. And thanks to this setup, we can now sniff the communications even with the main CPU in the bootloader mode. And so we, using a logic analyzer, we made a trace of the different commands exchanged after the SPI Rescue feature is used. And if you remember, the SPI Rescue will erase all the data on the Titan M. And so it means that the bootloader needs to reinitialize it. And here we can see that by sending the set root of trust command to the keymaster task, the bootloader is providing a new root of trust, which is called here digest. We made a Python script that will act as a driver to convert the packets, the SPI packets, into commands that we then send to a parser that is using the protobuf definition in order to print the comments in the nice way. Now, can we send commands using this setup? And the short answer is no, not as is. Indeed, the SPI is not multi-controller. In this setup, the controller is the main CPU and the Titan M is the peripheral. And with SPI, there can only be one controller. One controller can speak with several peripherals, but one peripheral can only speak to one controller. So we need to multiplex the bus for a second controller. And to simplify what we did, we place an interrupter to switch the controller from the main CPU to the second controller, which is a Raspberry Pi we are using to communicate on the SPI bus. And something else we had to do was to use a level shifter to adapt the voltage, because the Raspberry Pi is using by default a higher voltage than the Titan M. So we ended up with this setup. You can see on the left, on the picture of the left. We have an interrupter, a physical interrupter that we can use to manually switch from one controller, the main CPU, to the other one, our Raspberry Pi. And so thanks to this setup, we can now send commands to the Titan M even when the main CPU is in the bootloader mode. And as you will see, we use this setup, in fact, to exploit one of the vulnerabilities we are going to present. So I'm not going, now I'm going to present some vulnerabilities we discovered and how we exploited them. And the first vulnerability we found is an out-of-bound read impacting the command UART pass-through from the nuggets task. And the particularity of this bug is that it can only be triggered when the main CPU is in bootloader mode. This is why the setup I just presented is in fact very useful when it comes to exploiting this vulnerability. And in this case, in the case of this command, the index, that you can see is the argument of this function and is controlled by the attacker. There is only one check on this index. It has to be different from the value passed through. And when it is used as the index of a string array to retrieve a string. And this string is going to be printed on the UART. So as you can see on the string array that is on the right, there are only 5 strings. So if we use a higher value than 5, we will in fact tell the system to print a string at another address. So we can use this vulnerability to leak informations, to leak data on the UART. So there are several addresses that are interested. For example, some are in fact hardware registers, and they can contain interesting data. But the ones that we really targeted are the addresses close to 0, because if you remember, at the address 0 there is the boot ROM, and it means that we can leak parts of the boot ROM thanks to this vulnerability. There is one limitation. It is that the system is going to print a string and not a bytes array. So we can only leak parts of the boot ROM using this vulnerability. A second vulnerability we discovered is a downgrade issue. It seems that there is an anti-downgrade mechanism that is implemented but not used. Indeed, the boot ROM and the loader, when verifying the signature at boot, they will take into account a value that is coming from a hardware region that is called ifuse. And this region is supposed to be updated each time there is a new firmware that is installed, updated on the chip. And this is not, in fact, updated. This value is never updated. And it means that we can downgrade to any old firmware using the SPI rescue feature. So can we use this vulnerability and exploit a known vulnerability from an old firmware in order to, let's say, find a better leak or simply execute code on the chip? And the answer is yes, but it's not that easy. Indeed, the Android security bulletins contains details about all the CVEs impacting AOSP, but also the Pixel devices. However, it is hard to find the details. The details are not sufficient to identify clearly the vulnerabilities that are impacting the Titan M. And so this is why the vulnerability we are presenting now has we present three CVE numbers because we cannot tell precisely which one it is. So this vulnerability is impacting the command IC push reader search from the identity task. And it is a classical buffer overflow, the kind of overflow you study at school. And in this case, if you look at the man copy line, the variables pubkey ADDR and pubkey size are controlled by the attacker. In fact, pubkey IDDR is pointing onto a buffer that is also controlled by the attacker, and it's computed from the buffer address and an offset that is also controlled by the attacker. So this function will copy values from this buffer into the global variable that is called IC struct. And after this IC struct variable, there are some interesting data, such as the runtime data of the chip or the list of command handlers that are in fact pointers that the system will use whenever a command is sent to the chip. The system will retrieve the corresponding pointer and execute the code that is there. It means that if we can overwrite, let's say, AVB get state with a pointer of our choice that points to a region, memory region that is executable and that contains the code we want to be executed, then the system will execute it after we send AVB get state command. So basically, we gain code execution thanks to this vulnerability. So we modified our nose client in order to exploit this vulnerability. And because we could not find the proper way to reconfigure the MPU, we had to reuse the code that is already present in the system. We cannot turn a memory page both writable and executable, so we have to use rob chains in our exploit. But it's still very interesting, this vulnerability, and we can do a lot of things thanks to it. And for example, we implemented a leak function in our client that leaks arbitrary data from the memory. And this is quite helpful for debugging, but it also allows us to dump the full boot ROM this time. And we can also use this vulnerability to leak critical information such as the root of trust. And it could have been used, in fact, leaking the root of trust and the salt from StrongBox could have been used to decrypt the key blobs and break StrongBox. But if you remember the SPI rescue feature that we need to use to exploit this one-day vulnerability, it erases the data present on the Titan M, and so it also erases the salt. So this is not really applicable in this case. So to conclude on the vulnerabilities, we reported these two vulnerabilities to Google, and they are not fixed. So now I'm going to let Damiano speak about fuzzing for more vulnerabilities.
So to find new vulnerabilities on Titan M in an automatic way, we wanted to explore how to use fuzzing, so how to fuzz the chip and see what results we can get. Titan M is not exactly the easiest of the targets for a fuzzer, since it is closed by design and does not really give any visibility over its internals. The only option we have is to use it as an oracle and call the library function to send a message and judge what happened from the return code of this call. So since we know well how the chip communicates with Android, this is actually possible. And we also know the format of the messages since it is open source. So we decided to adopt a mutation-based approach. We integrated libprotobuf mutator in our client, and we ran in total 2 fuzzing campaigns. The first one on an old version of the firmware is the last one of last year, And in this version, we managed to find 2 buffer overflows. One of them is actually the one that Max just showed how to exploit. So essentially, we managed to replicate the findings that we had found with static reversing. We also found 7 other vulnerabilities that either make the chip reboot or crash, or in general reach an invalid state. So this proves that the approach indeed is interesting, can work. So we ran a second campaign on the latest version of the firmware, and there we found that 2 bugs were still present. And by using the read primitive that we built upon the exploit of the known vulnerability, we inspected the memory around the code that was crashing, and we understood that the 2 commands were calling the same function that was doing a null pointer dereference. So this is a great use case for that read primitive. We managed to see that that structure was indeed not initialized when the code was reaching it. So we reported these bugs, and Google considered them not severe enough to end up in the bulletin. So this is the results. But in general, we are showing that the fuzzer is giving new results and interesting results. So a few comments. Again, all these bugs were found after really few seconds of fuzzing. So after these first findings, nothing happened afterwards. So this is on the one hand interesting because it means we are visiting some interesting code paths, but at the same time we might be encountering one of the main issues of black box fuzzers. That is to only be able to scratch the surface of targets and only be able to exercise shallow states. So this is a result of not having any coverage, and to improve that, we can try to build a picture of what happened after a command by not only reading the return code, but also parsing the actual response. This we can do it from the response that is given to the command, or parsing the UART log, which, however, requires to change the fuzzer architecture a little bit. So this is a first idea to try to improve and have a bit of visibility over what happened after a command. The alternative is to change completely approach and adopt an emulation-based solution. In that case, we would encounter a different range of problems because it is really a completely different approach, but it is definitely worth being explored. In any case, it is hard to turn the grammar awareness that our fuzzer is built upon into protocol awareness. So being able to simulate complex sequences of messages and interactions with the chip. That is, will always be a bit hard for a fuzzer and will require some cost of development. So to conclude this talk, we started from the firmware, and we found some interesting properties. The design and in general the choices behind security seem solid, but there are some debatable measures, such as that hard-coded canary. We developed and shared with the community some tools to interact with the chip, and also on the hardware side there is some work that some researchers can do if they are willing to explore this new module. And we also managed to use a known vulnerability to leak the boot ROM and mount what is actually the first code execution exploit known on the Titan M. Finally, we also explored how to use fuzzing. We managed to get some interesting results, but we also have some ideas on how to improve that and perhaps find even more interesting results. So at the link that you have in the slide, you will find our tools open sourced, and that is it for this talk. Thank you very much for your attendance, and we are happy to take any question.